isomer derives from two different kind of meanings. Iso is the prefix that means same, mers means parts. So when we talk about isomers, we're looking at molecules or something else that has the same parts, but in yet some way, shape, or form they are different. Now, the typical introduction is we start with structural isomers. I'm going to assume that you've already seen structural isomers. Structural isomers would be, for example, you have C4H10, you can have butane, or you can have 2-methylpropane. Both of those are C4H10, they're the same composition, but they're arranged differently, they're connected differently. In one, we have 4 carbons connected in a row, and the other we have 3 in a row with one branching off of the middle. So those are structural isomers. What we're going to look at today is configurational and conformational isomers. We're going to break down all of the words that relate to those, and then we're going to look at some descriptions of how to convert between structural, configurational, and conformational isomers, as well as what the difference in properties are between configurational and conformational isomers. So like I said, we're going to start by kind of going through some terms that relate to these things. So stereoisomers is our first term, and the definition of stereoisomers are any isomers that are the same connectivity and same composition, meaning that they're made of the same things, and that they're connected in the same order, but they differ in their arrangements in space. So in 3-dimensional space, these things are not the same. So an example of that are the 2 molecules that I have here, that I've built. So these are both composed of a black, a blue, a yellow, a white, and an orange atom, model kit atom. But, and they're connected the same. They're all carbon in the middle, connected to 4 separate things. But they're different in 3D space, and that's hard to see until you arrange it in the right form. So let's go ahead and put this like this. So here you can see now these are clearly mirror images of each other. So in other words, if I had a mirror plane moving up and down here and I put this up to it, it would see this. Okay, it would have the orange on the side closest to you, the blue on the side closest to me, the yellow going up and the white going away from the mirror. Okay. So these are mirror images of each other. And what that means is that because of that, I can't put them into the same spot. So if I try to align these so that they are imposed on one another, I try and put the yellows and the whites in the same spot, the blues and the oranges will be on opposite ends. If I rotate that and try and get it where the blues and the oranges are on the same ends, then the white and the yellows will not be. So it's impossible for me to make these the same in 3-dimensional space, unless I go ahead and do some changes to them. So these are an example of stereoisomers. Now, that's a very broad definition. And so if we put that in other terms, stereoisomers can be referred to as configurational isomers and conformational isomers. So we're going to go ahead and talk about what configurational isomers are, and then we'll talk about conformational later. So a configurational isomer is a compound that cannot be converted into another by rotation about a single bond. Okay. So if these 2 molecules had been different, but I could have just rotated something and made it into the other one, that would not have fit this definition. Okay. These are not the case. If I want to convert one of these into another, I'm going to have to actually break a bond and take these apart and put them back together. Okay. So that's our definition of configurational isomer, but that again does not probably give you a lot of credence into like what that actually is. So molecules that have the same composition, same connectivity, but they're different in their arrangements in 3-dimensional space, that cannot be converted via a single bond. So a better definition of these kind of gets into what the examples are. Enantiomers and Diastereomers are your 2 types of configurational isomers. And we don't know what either one of those is, so it's difficult to kind of comprehend what this is. So let's go a step deeper and look at enantiomers. So to look at enantiomers, we're going to kind of have 3 terms altogether. The first term is chiral. So the definition of chiral is non-superimposable mirror images. And this we've just seen. So these 2 molecules are chiral in that they are non-superimposable mirror images. Now, the mirror image thing you probably understand. Non-superimposable means I can't take these and I can't put them so that one goes on top of the other and they're identical. So these are not superimposable. One of the great examples of that that makes a lot of sense are hands. So hands are chiral. Your right and your left hand are kind of the same and kind of different. They are mirror images of each other, ignoring all the little imperfections. But for the most part, they're mirror images of each other, but they're not superimposable. If I try and put my hands on top of one another, then the thumbs are on the opposite sides and they're in the reverse order. Okay, so that would be the same thing as chiral. And then if you're coming from an organic chemistry background, you're looking for molecules with an R or an S designation. Those are chiral molecules. If you have R this or S that, that's going to be chiral. Now I assume you've seen how to designate R and S before, so if not, you might want to check into that before you go through the rest. But let's say that this is my 4th priority here. The blue is first, yellow is second, and orange is third. So to designate this, I would look and I go from blue to yellow to orange. I'm going in a clockwise rotation when the fourth thing is pointed away from me. So this would be an R configuration. And then in this one, if I point the white one away from me and I go from blue to yellow to orange, I'm going in a counterclockwise rotation. So this would be the S form. So both of those things separately are chiral. They are non-superimposable mirror images, and they have the R and the S designations. Okay? Now, anytime you have a molecule that has a carbon with 4 different groups attached to it, that will be chiral. Okay? So if you have multiples of those, that can get a little complicated. But if you have a single carbon with 4 different things attached, that will be chiral. Enantiomer goes with the word chiral. They're almost the same thing. So enantiomers are a pair of compounds that are non-superimposable mirror images. So chiral kind of refers to just the one thing, and an enantiomer refers to the pair of things that are the mirror images. This is chiral, these are enantiomers. Okay? So these are 2 compounds, same composition, same connectivity. One is the R designation, one is the S designation. Okay? So that's the kind of thing we're looking for. So examples of these would be HAMs, of course. But then we get into the organic chemistry, we would look at butanol. It's a really simple example of that. So if we draw butanol, we would have butane, which would be 4 carbons. And then on the second carbon, we're going to put an alcohol. So there's 2 ways to do that. Now if I put an OH like that, what I'm implying is that there's also, better job drawing that, there's also going to be a hydrogen like this. So this carbon here is chiral. It has a CH3 group, a C2H5 group, OH group, and an H group. So it's got 4 different things attached. And currently, we're looking at a case, oh, this is a little backwards. Let me draw the other one. We'll figure that one out first, it'll be a little easier. So if I draw the enantiomer to that, I'm going to reverse 2 of the positions. Let's go ahead and do that. So here we have the H pointed away from us. We would go priority 1, priority 2, priority 3. So we're looking at the R form. And then here we're going priority 1, priority 2, priority 3, but we're looking from the wrong side. So this is going to be the S form. So butanol has a pair of enantiomers depending on the positioning of that hydroxyl group with respect to the other 3 groups. 3-methylhexane is another one that's good. So here's our hexane. So at the 3rd carbon, if we put a methyl group, so we draw like this. Alright, I'm actually going to write in the CH3 in case that gets confusing. So this carbon here is chiral, and it will form a pair of enantiomers because I have a C2H5 group, a CH3 group, a C3H7 group, and an H group. So I have 4 different things. And this is the simplest chiral, pure hydrogen and carbon hydrocarbon. Okay? So this would have an R and an S form. This one would be the S form. So this would be S3-methylhexane. Okay. Now, why do we care about all of this is where we kind of go next. So let's add in one more term to describe this. The stereocenter is the actual point in the molecule where these chiralities are occurring. Technical definition is a point in the molecule where exchanging 2 atoms would form a stereoisomer. So what that means is this. I have these 2 enantiomers. Let me get that as a mirror image. So if I take any 2 of these things and I switch them, so I'm going to switch the blue and the yellow one here. When I switch their places, it will turn into the other thing. So I've gone from non-superimposable to the exact same molecule. So I've gone from R to S. I've formed a stereoisomer by switching that. So this point, this carbon, is a stereocenter. So you'll often see all 3 of those terms kind of work together. Stereocenter is the point in the molecule. The enantiomers are the pair of molecules that share this property. And the first term was chiral, and that is the kind of property of that each individual one of those molecules. So diastereomers is kind of your catch-all term. So diastereomers are 2 molecules that are different in the arrangement of 3 space, but are not the same connectivity, same composition, but they're not mirror images of one another. So essentially, what this definition is saying is this is saying they are configurational isomers. They're different in 3-dimensional space, but the same otherwise. But it's excluding enantiomers or chiral. second, where the whole molecule is scattered. So what things are different in 3D space that are not this 4 different group attached to a carbon arrangement? There are 2 kinds of that. One are the cis and trans, or the E and Z alkenes. Okay, so we built a couple of those. So this, here we've got a carbon-carbon double bond. We've got 2 orange groups on one side, 2 of the white groups on the other. Here I've got a carbon-carbon double bond, but I've got an orange and a white on one side and an orange and a white on the other. Now these are different in 3-dimensional space. They're the same connectivity, the same composition. It's both 2 carbons double bonded, and each carbon has an orange and a white attached. So the same connections, but they're different in 3-dimensional space clearly. And it's not an enantiomer, it's not chiral, so this would be considered a diastereomer. These are diastereomers. Okay? The other time that can happen, which is a little more complex than that, is if you have multiple chiral centers within a single bit. So let's say that this has 3 different groups attached, this has 3 different groups attached. Both of these have an R and an S configuration. Let's say hypothetically that one molecule has an R and an R configuration. If I have a second molecule that has an S and an S, those will be enantiomers. So those will be mirror images of one another. But if I have an S and an R, then that's not the case anymore. And therefore we have not enantiomers, but they are different in 3-dimensional space, so therefore these will be considered to be diastereomers. Okay. So kind of our theme here is that all of these things are different in 3-dimensional space, but the same otherwise. And that's kind of back to our isomer definition. It's the same, it's somehow different. So some things that come into play with these are, well, why would we care about that? Well, it turns out that chiral compounds can interact with other chiral compounds differently. So there was a case where there was this drug made called Polarimeter, and the R form of it did one thing, and the S form did something else. And so that ended up being really bad. And so we want to be able to analyze which of the forms we have and when that's going to be relevant. So a polarimeter is a machine that can measure what's called optical activity, which we'll define in a second. And it measures the angle of rotation of plane polarized light, which is something that these chiral compounds have an influence on. So let's go through, define that, and come back to this. So something that's optically active. Okay? So when a molecule causes plane polarized light to rotate, that's considered the definition of what optically active is. But you're probably not familiar with what most of that says. But if we have just the R form or just the S form of something, what happens is that molecule will have an effect on light. It will cause it to interact with the electric field of that light wave, and it will change it. It will change it in a colligative manner, where the more of it you have, the more it will change that light. So let me go ahead and show you what that looks like first. And then we'll come back and look at what a polarimeter is. Okay, so over here, I have some polarizing filters. The way that a polarizing filter works is it interacts with the electric fields of light. And hopefully you can note this. So if I put this over here, you can kind of see that there's still the white sphere behind me. Okay, but as I rotate this, what you're going to see is that it's going to change, and all of a sudden it's going to block out all the light behind these two. So what's happening there is that the filters are blocking out electric fields only in one direction. And when I rotate it, one is blocking out one direction, one's blocking out the other, and it blocks out all of the light. So when you put a chiral molecule after you polarize light, it will rotate that plane of polarization. Okay? So what that means is, I'm actually going to go over here and show you. So I can make a machine that will shine polarized light through, and then have a sample here, and then put a second filter here. Now normally, if I put this at 90 degrees to the first one, it's going to block out all that. But when I put my other compound here, what's going to happen is that's going to affect the light, and I'm going to need to rotate this to continue to block out all the light. Now the R form will cause it to rotate one way, S form will cause it to rotate the other way. But some way, somehow, I'll be able to block out the amount of light by rotating this through some angle. So what I can do is I can use a polarimeter, and I can set that second polarizing filter to rotate until I get back to the original point where I'm blocking out all the light. It can then report out how much it rotated as the angle of rotation. And that can be used to make a measurement about optical activity of a particularly chiral compound. So if we had that, a polarimeter is something that measures that by looking at this. here's your polarizing filter. We have light coming through. Normally, your second polarizing filter is at 90 degrees. I'm not sure how I'm going to draw that. So we're just going to pretend that's at 90 degrees to this one somehow, some way. But when I put my sample in the middle, that's going to affect that plane of that polarizing light. It's going to cause it to twist. So now I'm going to need to twist this in order to still block it. And so the angle of rotation is what that measures. Now, as I increase the amount of R form of this or S form of that, that's going to change that angle more and more. So I can make a measurement as to how much that's affecting that light. Okay. So that's how a polarimeter works. And that takes advantage of the optical activity of these configurational isomers, of these enantiomers. So a racemic mixture is when you'll have equal quantities of R and S. You'll have equal quantities of enantiomers. So you're going to have one of those rotating light one way, and the other one's going to rotate the plane of polarized light the other way. So when you have equal quantities, there's no optical activity of that mixture because your effects on light are essentially canceled out. Okay, so those are the configurational isomers, diastereomers, and enantiomers. Conformational isomers is kind of a different ballgame. So a conformational isomer is you're looking really just at one molecule now. You're not looking at two, you're not looking at pairs for the most part. But in this, you're looking at how a molecule will change as it rotates. So if I rotate this like this can become a much more crowded molecule than it is when it's like this. So depending on the placement of the hydrogen, the CH3 group here, and the OH group here, will change what this looks like. You can even have some little fighting going on. So conformational isomers are forms of a molecule that can be changed into one another via rotation about a single bond. Okay? So for this, you're probably going to get some experience in organic chemistry trying to say, okay, well, how should I view this molecule in order to really understand how that's changing when I do those rotations? And so a common thing to do for these are Newman projections. So in a Newman projection, let's take a really simple thing like ethane. Let's say we have an ethane, and let's say we have two hydrogens that are coming down, going into and out of the plane. The hydrogens going up are in the plane of the molecule. Okay? And let's say I stand over here and I stick my eyeball in. So I'm looking down at this carbon here through to this carbon, and I see all these hydrogens. So a Newman projection is a way to project what that actually looks like. So the front carbon, this one, gets represented by a dot. The back carbon gets represented by a circle. Okay. And then the hydrogens I would draw coming off of the dot. So from this dot, I would have the hydrogen coming up. I would have this one here would be, so I'm looking this way. This is out in front of the board, so it's to my left. So I would draw it coming out to the left. That's that one. And this one is coming out to the right. Okay, so that one I can tell because this one is behind the board. If I'm looking this way, behind the board is to my right. So when I rotate my view this way, now I'm going down and to the right. This one has the same hydrogen coming up. So I would draw coming off the circle another hydrogen. I'm just going to put it a little to the side so we have room. This one is coming off to the side as well. So that was this one here, this one here. But double dots there. All right. And then triple dots. This one is going to be off to the left, which is going to be right here. So this is the Newman projection. This is essentially me representing this carbon here is this carbon here is this, and then where all my position groups are. So this is called the eclipsed form, where all the hydrogens are kind of aligned together. I can change that and make that into what's called staggered form. So I can have one hydrogen coming up, just like I had before, but for the back carbon, I'm going to rotate it and end up with this. So these are conformational isomers. It's the same molecule. I've just rotated that bond by, what, 60 degrees? So here, now I've changed it. Now, what I have going for me then is that these groups here are very close together. You can't tell that so much with a model kit, but if you represent them accurately as atoms, that's really a tight configuration. And especially if I get something larger than a hydrogen attached to something. So, eclipsed. So if I get into the staggered form, I've rotated that bond, and now I end up with this picture. And then what would be a good challenge is to go back and say, okay, how would you change your drawing to make, so we can go through and say, okay, so in this one, Now I have my carbon and carbon that I'm looking down. Let's assume my I is in the same place. So now I'm seeing a hydrogen up and to the top. This hydrogen is to my right here, facing this way. So facing this way, right would be behind the board. And then this one is off to my left. So it would be in front of the board, my I pointing this way down the molecule. But these ones are now changed. So if I take this one, put 4 dots on this. So for here, I'm going up and to the left. So if I rotate, so my I is going this way, up and to the left is going to be in front of the board. So I would draw a wedge, like that. This one, the little triangle there, is going to be up and to the left. And then this hydrogen here is going to be going down and in the plane of the 2 carbons. Okay, so conformational isomers are different than configurational. It's really about the same molecule. I'm just changing how it's arranged in 3D space. Okay. So we have configurational isomers, which are enantiomers and diastereomers, conformational isomers, and then of course structural isomers. So if I want to change between one or the other, so if I have a structural isomer, I actually need to break a bond somewhere, or multiple bonds, and form new bonds. If I want to change between an R and S form, I'm going to need to break bonds and form new bonds. But for a conformational isomer, I don't need to do that. Conformational isomer, I'm going to do a rotation. And that's going to be about a sigma bond or a single bond. So you can't do a rotation if you have a pi bond in place locking that molecule in. When I have a double bond, this is going to prevent me from being able to do any reasonably sized rotation. But if I have single bonds, these rotations are occurring all the time. Okay, so this will be going on as this is going on, as this is going on. And all of these things will be rotating pretty rapidly. Okay. That's how you convert between the ones. And then, how do their properties compare? Now, structural isomers, those are literally different chemicals. So they're going to have different physical properties. They're going to have different melting points. And they're also going to have different chemical properties. They might have similar, because you have the same pieces, but they might be totally different. You might have an ether and an alcohol. So they're going to have different physical chemical properties. They're going to have different intermolecular forces, and they're going to have different chemical properties as well. They're going to react differently because they're different chemicals. Now, conformational isomers, that's not really the case anymore. Now, conformational isomers, we need to be careful. There is a difference between this conformation here and this conformation here that's very crowded for this molecule. But if you're looking at a bulk property like melting point, that's irrelevant because all of those molecules are continually changing where they are. So I would say that for conformational isomers, these would have the same chemical and physical properties. But have an understanding that that's describing the bulk material where I have, you know, quadrillions of these or quintillions or sextillions of these. So that's different than, say, looking at a single individual molecule. There will be energy differences between this on the single molecule level, but for any bulk properties, those will all be the same because we're looking at essentially the same molecule. We're just doing a rotation. Now, configurational isomers, those are the same composition, same connectivity, so those will have the same chemical properties. And they'll have the same physical properties. There are some exceptions to that. Okay. First of all, for the chemical properties, these will be different with other chiral materials. A good example of that is going back to hands. Your hands are chiral. Which one you use might not matter for this and that. But if you have a glove, if the glove itself is chiral, just like your hands are, then you have to use the right-handed glove on your right hand. There are some gloves where it's symmetrical. Like they put the thumb out to the side. And so therefore it doesn't matter whether you put it on your right hand or your left hand. But if the glove itself is similar to your hand, then it's going to matter which one you use. So likewise, enantiomers, in R or S form, doesn't matter which one you have for most reactions. But if you're reacting with something else that's chiral, which happens a lot in biochemistry, then it's going to matter which one you have. And so most of the things like separations of chiral materials need to involve some kind of biochemical route to happen. So they're going to pass it through some organism. Okay? The same physical properties, that's true except for rotation of polarized light. It's going to be different whether you're in the R form or the S form. And as I'm going through this, I'm really not talking about configurational isomers. I'm talking about enantiomers here. For diastereomers, a lot of this becomes different. So if we're looking at the Z form or the E form of a chemical, there would be small differences in their chemical and physical properties. If we're looking at the RS and the RR form, there would be small differences in their chemical and physical properties beyond this. But for enantiomers, that would be the case. Now, we can separate based on these interactions. So maybe we can construe that a little bit as a physical property as well. I would consider it to be the chemical